Today we have problem 3 from the general round of the Harvard MIT math tournament this year, where we're given that Ashley wants to fill each cell of a 3x3 grid with some of the numbers 1, 2, 3, and 4, possibly none or several, and we want to find the way, or find the number of ways that she can do so, such that each row and each column all contain each of 1, 2, 3, and 4 exactly once. And we have an example grid here where, see, in this row we have 1, 2, 3, 4, second row 1, 2, 3, 4, third row 1, 2, 3, 4, and then first column 1, 2, 3, 4, second column 1, 2, 3, 4, third column 1, 2, 3, 4. And so how do we want to count? Let me draw an empty grid here. And so usually with counting problems, I guess you want to try casework. And in this case, I guess you might want to try casework based on, how many numbers are in one cell. Like for instance, in the first row, one case might be maybe you have all 4 numbers in one cell, and then so this row and this column are immediately taken care of, and then you try to look at this subgrid. Another case might be maybe you only have 3 numbers in one, right? So like 1, 2, 3, and then maybe you have like a 4 here, or the 4 could be here, right? And then you do casework on the rest. And then I guess the last case would be, or 2 more cases, 2 numbers in one square, and then the other 2 are separate, so like this, or they might be together like this. But if you try this, you'll see that the casework gets really, really messy, and it'll take like a very long time, and it'll be very prone to error. So you want to try to find a, I guess, smarter way to count. And the idea is, right, we want to find the number of ways such that 1, 2, 3, and 4, each of those appears in each row and each column exactly once. But note that, where we place the 1 doesn't really affect where we place the 2's, which doesn't really affect where we place the 3 or the 4's. So this sort of means that, we can come to the conclusion that they are independent, right? The number of ways to place the 1's are independent from the number of ways to place the 2's, the 3's, and the 4's, etc. So if we can find the number of ways to place a 1, something like this, such that each row and each column have a 1, then, identically, placing the 2's, 3's, and 4's all have the same number of ways, and then we can just multiply them all together to get our answer. Right, so how many ways are there to place the 1's? Well, we can just go row by row now, right? In the first row, there's 3 places to place the 1, right? Let's say, without loss of generality, let's just place it there. And placing it here gets rid of this column, right? Or placing it here gets rid of this column. So in the second row, we only have 2 spaces left to place it. So let's say we place it here, then this gets rid of that column, or the last column, and so in the last row when we place it, there's only 1 place to put it now. And so multiplying all these together gives us 6 ways to place a 1. And again, identically, we get 6 ways to place a 2, 6 ways to place a 3, and 6 ways to place a 4. And again, because they are independent of each other, the total number of ways to place 1, 2, 3s, and 4's in each cell, so that each row and each column has a 1, 2, 3, and 4 is just 6 to the 4. 6 to the 4th, or 1,296 ways. And that's our answer.